Hi, this is Caroline, and today I will be presenting Lab 5, which is Faraday's Law. The purpose of this lab is to observe a bar magnet falling through an aluminum foil tube, and we modeled this interaction computationally on GlowScript and used Faraday's Law to compare the results of the computational model and the real-life experiment. So we know that the time-varying magnetic fields provides an EMF that creates a current, and in this lab the falling bar magnet provided the source of the magnetic field and therefore the induced current, which goes around the tube. In this lab, the average time for the magnet to fall through the tube in the actual experiment was about 1.7 seconds, and computationally was about 3.99 seconds. So the physics principles used in this lab were the Biot-Savart law, which just computes the magnetic field of the bar magnet. The most important concept was Faraday's law, which says that a changing magnetic field, which in this case is the bar magnet or caused by the bar magnet, induces a current in surrounding objects, specifically conductors, and in this lab the aluminum foil contains the current. We know that flux is equal to the magnetic field times the area, and we also know EMF, that's Faraday's law, and then electric potential is equal to the current times the resistance. We also know Newton's second and third laws, which just states net force is equal to mass times its acceleration, and then the equal and opposite reacting forces for every force. Lenz's law also states that the induced current will flow in the direction where the magnetic field will oppose the direction of the change in flux. So the experiment itself, we used the magnetometer app to determine which end of the bar magnet was oriented towards the north, and then we dropped the bar magnet through the tube of aluminum foil held vertically. We know that the length of the tube was about 30 centimeters and the mass of the magnet was about 23 grams. Using a phone to film this, I was able to scrub through the video to find the exact time the magnet dropped through the tube. And after repeating this 5 times, I found that experimentally it took about 1.67 seconds, and computationally the model said it was 3.99 seconds. So this was my GlowScript code. The first step was to obtain the geometry of the tube, which had a length of 30 centimeters and a width of 1 centimeter. Then we created a function to compute the magnetic field of the bar magnet using the Biot-Savart law from the code used in Lab 3. Then the magnetic flux was calculated, which is just the change in magnetic field times the number of rings or loops. Change in flux. Then the net force on the magnet was calculated, and the magnet's position and velocity were updated and then plotted on the graph, which will be shown on the next slide. And here's my GlowScript graph and computational model. And the result of the GlowScript code was that it took about 3.99 seconds to fall through the tube, which is a little larger than my experimental result. So in this simulation, we know that blue is counterclockwise and red is clockwise to show the direction of the current around the tube. We also know that should we flip the magnet around, the motion of the magnitude stay about the same, but the current flips because the change in flux flips. We also know that the magnet should fall slower in real life because we do not account for air resistance and other external factors in the computational model, which would make the computational model more accurate if we accounted for air resistance, resistivity in the conductor, and if we used a more accurate mu mag, which I just used mine from Lab 3. And then also the velocity versus time plot shows that while in the tube the velocity is constant because the acceleration is 0 and all the forces on the magnet are constant. This is when magnetic force and gravitational force on the falling magnet becomes zero or equal each other because the bar magnet stops accelerating when it reaches terminal velocity. Then, not in the tube, the velocity has a negative slope, which means the forces are increasing in the negative direction, and we also know that velocity is negative, signifying that the force of gravity is stronger than the upwards force, which is the magnetic force. If the resistivity of the conductor were reduced, the magnet would fall less quickly through the tube as the resistance decreases, and if holes or slots were cut into the tube, the magnet would fall faster because of reduced number of rings. The induced current is also reduced, which decreases the magnetic force acting on the falling magnet due to the tube of the aluminum foil. All right, thank you for listening to Faraday's Law Lab.